Okay, now we're going to do what is my favorite approach to training deep graphical models, and that is pseudo likelihood. And we're also going to do a closely related thing that Hinton came up with about 10 years ago that got a lot of attention, but turns out to be essentially the same as pseudo likelihood. But for historical reasons, it's good to just mention it and see how it ends up being equivalent to pseudo likelihood. So what's going on in pseudo likelihood is that the loss function that we would like to train on is this exponential softmax. And the exponential softmax is itself intractable. We can't really compute the probabilities under that distribution because the partition function z involves this exponentially sized sum that we can't compute. Pseudo likelihood is going to get around that problem by defining a different measure of probabilities called the pseudo likelihoods. They're likelihoods because they depend on they're focusing on the dependence on the parameter vector. And it's going to have some nice, and if we replace our objective function with pseudo likelihood, we can then effectively optimize that objective function. And there are nice theorems that say that if you optimize that objective function under universal expressivity assumptions, you will recover the correct population distribution. So let's go through that. So the first thing I'm going to do is introduce some notation. This notation is the same as we saw in Gibbs sampling. So if I've got graph coloring y, this is going to be the coloring of the nodes other than the node n. So we're going to take the color of n out of this. This is going to be the coloring restricted to the neighbors of n, just the Markov blanket around n. And now we're going to define the pseudo likelihood. So I've got a coloring, and I want to define a likelihood that I can compute efficiently. So what I'm going to do to approximate the probability of y is to take a product over all nodes of a probability of the gold label value of that node. Okay, so how am I going to measure the probability of the gold value of that node, the gold color of that node? What I'm going to do is I'm going to take the coloring and take the node n out. Look at the color, all the colors other than n. And I'm going to look at the conditional probability of this coloring given all of the other colorings. And then I'm going to take the product over all nodes of that conditional probability. So it has sort of the right units, right? It's taking a product over all the nodes of a probability of that node. So it sort of has the right units and scale for a probability of the coloring. Now this conditional probability, the same thing is going to happen here that happened in Gibbs sampling. This conditional probability doesn't need to really look at all the colors other than n. It only needs to look at the ones that are connected through an edge to n, the local Markov blanket of n. And now all we're going to do is we're going to change our optimization algorithm by replacing our loss function by the pseudo likelihood loss function. And this is going to be tractable. And now there's this nice theorem associated with pseudo likelihood, which is if I assume universal expressivity. So I assume that the model I'm training can be any distribution, right? So assume it can be any distribution. And in that case, we're looking at the argument over all distributions of this pseudo likelihood loss function on that distribution. And so let's consider the argument over all distributions of this loss function. And the claim is that that argument over all distributions is equal to the population distribution or whatever distribution we're sampling from. Could be the training distribution, but I'll work with the population distribution here. Okay, so to prove this theorem, I should point out this is a lot like the cross entropy theorem, right? In the cross entropy theorem, we said that if our model was universally expressive, then the cross entropy loss also has this property, that its optimum is the population. So this is saying that the pseudo likelihood has that same property for this tractable approximation of the model probability. So to prove this theorem, it suffices to show that the population distribution itself, when measured by the pseudo likelihood, so this is saying, suppose I took the population distribution and measured its loss using the pseudo likelihood, that's less than or equal to the objective function for any other distribution Q, right? So if that's true, if this value, if I stick pop into here, if that's less than any other distribution, then pop is the minimizer. That's just sort of saying what it means to be the minimizer. So let's look at this. I'm going to do a proof for the case of 2 nodes. The case for a large number of nodes is going to be essentially the same, but let's do the case of just 2 nodes. So what's my pseudo likelihood optimization problem? I'm minimizing over all distributions Q, the expectation over the population of minus log, and now this is a product of the 2 conditional probabilities, right? So the probability of the first node given the second, and the second node given the first. So the first thing I'm going to do is I'm going to say, well, I can relax this problem and put in 2 arbitrary conditional probabilities here. You know, a P1 conditional probability and a P2 conditional probability. And now I'm going to relax it and say P1 doesn't have to have anything to do with P2. I'm just going to make this 2 separate conditional probability distributions. In that case, I've relaxed the problem, so there are more pairs P1, P2 than there are Q. So because I've got more choices here, it has to go down when I minimize. So this has to be at least as large as this optimization problem where I've decoupled them. Now this log of a product becomes a sum of logs, and this expectation can be pushed into that sum of logs. And the minimization problem then can minimize the P1 and the P2 independently. But if we look at this, we know that the optimum for this can be viewed as a kind of cross entropy loss. The optimum for this is just this one first problem, is just the population distribution. And that's true for this also. So when I minimize over P1, I get the population. When I minimize over P2, I get the population. And now when I recombine this into the product of those 2, I get the pseudo likelihood of the population. So what I've argued is that yes, the pseudo likelihood objective of the population is always less than or equal to any other distribution, or this minimizer. So I find this to be a reasonably compelling justification. Okay, contrastive divergence. So in contrastive divergence, we look at MC-MC sampling, and we think of MC-MC sampling as a way of getting a sample from the model's distribution. But instead of starting from an arbitrary point at running MC-MC to its stationary distribution, we're going to say, well, look, the gold standard Y in our data or in our population is drawn from the distribution we want. So why don't we just start our MC-MC process from the gold label? And since the gold label is drawn from the distribution of interest, when I average over a large number of those, I'm essentially sampling from the population distribution. And I want my model distribution to be the same as the population distribution. So I'm going to sort of hot start the MC-MC process by starting it at the gold label. So I start the MC-MC process at the gold label, and then I run it for k steps. And after I run for k steps, I look at where I am. So I started at some graph coloring, I run for k steps, I get some other graph coloring, and then the loss is going to be the score of where I got to minus the score of my original gold label. So the intuition is that if my model's wrong, then when I run for some number of steps, I'm moving into the wrong distribution. So I would like to, so I'm thinking of this as a good label, and this is a bad label, and I want to move toward my good label. That wasn't very clear, but let me say something else that might be clearer. Suppose that the model distribution converged to be the correct distribution. In that case, the MC-MC, we're starting by drawing from a distribution, and if the models converge to the correct distribution, the stationary distribution of this MC-MC process is the data distribution. So when I do a few steps, I'm drawing, then y prime is drawn from the same distribution, because I'm drawing from, if the model's correct, I'm drawing from the correct distribution, which is the stationary distribution of the model, then running for k steps to get another point, but I started from the stationary distribution. So the expectation, so this is essentially being drawn from the same distribution, in which case the expected difference in these scores is 0. So the gradient of this function will be 0 when the model is correct. And this is saying we want to reduce the score of the thing that's probably wrong and increase the score of the probability of the thing that's right, since we're moving down the loss. So another way to think about this is it's trying to move from the wrong one to the right one. Okay, now there's a theorem associated with contrastive divergence, which is if you take the Gibbs process, that's an MC-MC process whose stationary distribution is the Gibbs distribution. We're aiming at making the stationary distribution the correct distribution. It's an MC-MC process for sampling from the model distribution. Okay, so we take Gibbs CD1. CD1 means we take the Gibbs MC-MC process and we take one step of the MC-MC process to get our y prime. Now, if we're taking one step of the MC-MC process, it means we're when we do one step, we're taking a random node and assigning it a new value according to the local Gibbs distribution on that value. So we're drawing y from, we're taking a gold label y, and we're drawing the color of a node n, where we draw n at random. We're taking the color of node n from the conditional probability given the other colors. So you can see that this is like, in some sense, like pseudo likelihood. And y with that node set to this to the value drawn here is our bad label that we're going to try to move away from and move toward the good label, reduce this score and increase that score. So the theorem is going to be that this Gibbs CD1 contrastive divergence algorithm has exactly the same direction of update in expectation as pseudo likelihood. So so what I'm going to do is write down the pseudo likelihood training objective and just massage it and show that its expectation is in the same direction as Gibbs contrastive divergence 1. So here's the pseudo likelihood objective. It's an expectation over drawing from in this case, the training data. And in pseudo likelihood, we're going to sum over the nodes the negative log probability of the value assigned to that node given the other nodes. Okay, and the advantage of pseudo likelihood is that this becomes a tractable computation. So I'm going to write this here as the sum over nodes of minus log, and this probability is the e to the score over a partition function. But in this case, the partition function only has as many terms as there are possible colors for this node, right? Because we're defining a distribution on the colors for this nodes. So this z is a sum over the possible colors of this exponential. And these things are easily computed. We can compute the scores. So now we've got a partition function that's easily computed, that's specific to each node. So I'm just massaging this. This becomes log z minus the score of y, right? I'm just doing that. Then I take the gradient. And when I take the gradient of log z, it becomes 1 over z times the gradient of z. And the gradient of z is a sum over y prime of e to the score. And so when I take the derivative, that stays the same. And I get the gradient with respect to phi of this score. And I've still got this term over here. So when I take the gradient, the gradient goes in and I get it in here also. Okay, so now if I take this 1 over z and move it inside that sum, then the product of 1 over z and this becomes the probability that n has the value y prime given the other nodes. Okay, so we're just back to having the probability here and the gradient of the score. So I've just copied that first line over here. So this is where we were. We're still analyzing the gradient of the pseudo likelihood loss. So this sum over y, the probability times this is just the expectation over y drawn from this conditional probability of its value given the rest of this gradient. Now that expectation over y, this sum over n is going to give me something that's proportional to the expectation over n. I'm drawing n at random, so if I multiply this by 1 over n, I get the expectation over n. So now I've got the expectation over n and the expectation over y drawn from the conditional probability, which is one step of Gibbs sampling of the gradient of the score after I do the update, minus the score before I did the update, which is exactly the Gibbs, this difference is exactly the Gibbs loss. So this is the gradient under phi of the Gibbs loss. So we've established this equivalence between contrastive divergence 1 under the Gibbs MCMC process and the pseudo likelihood objective. So I just want to emphasize again that pseudo likelihood is probably my favorite training method for deep graphical models. And the theorem associated with pseudo likelihood is has the same form as the theorem associated with the cross entropy loss, meaning that its optimum is the correct distribution if we assume universal expressivity. Okay, thank you. I'll stop there.